All right, so let's do this. It's not that long. Let's start. So, neural networks. Neural networks can be constructed using Torch NN package. Note that you have a glimpse of autograd. NN depends on autograd. To define models and differentiate them, an NN module contains layers and a method for input that returns the output. For example, look at this network that classifies digit images. So we need to learn this, but I know a little bit about this convolutions. We have a smaller, but we have feature maps, smaller image that feature maps, subsampling, convolution, subsampling, fully connected layer, fully connected, and Gaussian connections, and an output of 10. All right, it's like flat, right? Fully connected. ComNet. Okay, what do we note here? We know that NN depends on autograd. We're going to know that. We're going to know that the NN module contains layers and a method forward with the input that returns the output. For example, okay, that we don't know that. ComNet. It is a simple feed-forward network. It takes the input, feeds it through several layers, one after the other, and then finally gives the output. A typical training procedure for a neural network is as follows. Define the neural network that has some learnable parameters or weights. Iterate over a dataset of inputs. Process input through the network. Compute the loss. How far is the output from being correct? Propagate gradients back into the network parameters. Update the weight of the network, typically using a simple update rule. Weight equal to weight minus learning rate times gradient. Okay, this is like gold. I'm going to know this because this is awesome. But I'm gonna give it up to you. No. Can we do multiple? Yes, we do. And I fucked up. Okay, hold on. Awesome. We have it. And it did work. Wow. It doesn't matter. We have the note. Define the network. Let's define this network. Right, let's go through this code. So you have the usual import torch, import torch NN, the neural network module or library module. Is it a module or a library? Just torch neural network functional as f. And now let's define the network. We extend from the module class and we define the function init. And let's see, super net self dot init. It says 1 input image channel, 6 output channels, 3 by 3 square convolutional kernel. Let's read that again. So we have 1 input image channel, 6 output channels, so that is this 6 here, and 3 square convolutional. Is it this? Is it that? Then this is the input of the channels, output channel, and the, how is it called? I know it's called something. This number, but I don't remember. This is an affine operation. Y equals to weights time x plus b, linear. Is it a linear? Affine operation. So we have self.com1 equal to nn.com to d, convolutional to d, 1, 6, 3. For you that doesn't know convolutionals, I have a really cool article about this. It's on mine. This one, really cool. I don't think we have the time to read this today. We might read this in the future. It has really cool information, right? That is oh, this wasn't it. Hold on. Deep.ai. Go to deep.ai and search it there. Right, so let's note this, that we have input channels, output channels, and kernel size. Great. So we have second convolution 2D with 6 input channels, 16 output, and 3. Now we have the linear, that's an affine function. So you have self, fully convolutional, and neural network, linear. I'm going to copy this so we don't waste that much time. To have 16 times 6 times 6. What is that? It says 6 by 6 from image dimension. And 120. Is that the output? I think that is the output. So input, output. Yeah. Self.fully convolutional 2 equals to, we have this already. We change this to 2, and we put here 120, 84. The third one, we have 84 and 10. So this is the output where we're going to check if we are right or not. Now let's define the forward pass. So we return the self. I read this wrong here. Self Then we have the x. Okay. X equals to f dot max pull to d f dot value self.com1. I'm writing this in a moment. Let's try to make sense of this. So what do we have here? We have a max pool 2D, a value, and the result and the result of the first convolution for the input at the forward. And the 2x2 is the kernel size for the max pooling operation. You can go to deep.ai, the same deep.net, deep.ai, deepai.org, and search max pool, and there is a really good article about it. In the next we might be looking at that. Max pool, convolutionals, and other functions that are in neural networks. All right. Great. Let's continue with a second one of this. This time, use the same thing, but we use the second convolution and the kernel size of 2. So second convolution, this is because we change the parameters in each one, and a 2 here. This says max pooling over a 2x2 window. If the size is a square, you can only specify a single number. All right. Nice to know. Now we have the third thing is to say x view. What does this means? -1 self.num lat featureless. Wasze. Featureless. Feature. How do you say that? Okay, let's see what xview does. So allows a tensor to be view of an existing tensor. View tensors are the same underlying data with its base tensor, support view of explicit data copy, thus allow us to do fast and memory efficient reshaping, slicing, and element-wise operations. For example, to get a view of an existing tensor T, you can call t.view. Alright, so it's a different way of viewing the x tensor and doing operations with it. So finally, we do x value self.fully convolutional 1 x and x equal to f.value self.fully convolutional 2 x and x equal to self.fully convolutional 3. We don't do value in the last one, and finally we return the x. I'm gonna drink a little water here. All right. So def num flat features self x size equal to x size all the dimensions except the batch dimension. Okay. Num features for s in size. Num features features equal times s return num features. Okay, so what we are doing here is features and size for s in size, no features time s. We're multiplying. All right, with the x, the features num flat features. Okay. Within any given thing. Oh, we're using that here. Okay, I get it now. All right. Now we initiate this class. And also we have the first convolutional. It's with input of 1 channel, output 6 channel with a kernel size of 3 by 3 and a stride of 1 by 1. Then the second convolutional, input 6, output 16. Over here. Okay. Then 3 linear layers. All right. Also, let's see where. Now, you should have to define the forward function and backward function where gradients are computed. It's automatically defined for you using autograd. You can use any of the tensor operation, the forward function. The learnable parameters of the model are returned by net.parameters. Okay, let's read this again. You should have to define the forward function. Okay. And the backward function. Sorry about that. Where gradients are computed. Is automatically defined for you using autograd. All right. So you only define the forward. You only need to define the forward function. The backward, it's auto-defined by Pytorch. You can use any of the tensor operations in the forward function. The learnable parameters of a model are returned by net.parameters. Okay, params equal to list net.parameters print plan params print params size and see what size. So we have 10 parameters and the 0 is 6133. All right. We have the same here, so we are in the clear. Let's try a random 32 by 32 input. Note expected input size of this network, of this network, LeNet. Okay, maybe it's called that. Is 32 by 32. To use this network on the MNIST dataset, please resize the images from the dataset to 32 by 32. Okay. Let me do something. Okay, where were we? Okay, let's do that. Input equal to torch dot rand rand number 3232. So that's our batch. Out is the network input. Set network input. You have print out. We're going to have 10 numbers of the probability, and we're going to have gibberish basically, because it's all fresh. Great. 0 the gradients buffer of all parameters and backprop with random gradient. 0 the gradient buffer of all parameters and backprop with random gradients. Let's note this because I don't quite know what 0 the gradient buffer means, but net.0 grad, this, as the text said, it zeros the buffer gradient. And we're going to try to out.backward torch rand. Oh, we go backward with random gradient error 110. So we're going to go. Awesome. Let's continue reading this. So we have a note here. Torch NN only supports mini batches. The entire Torch NN package only supports inputs that are a mini batch of samples and not a single sample. Really good note here. For example, NN-com2D will take in a 4D tensor of ND sample, N channels, height, and width. If you have a single sample, you should use input on squeeze 0 to add a fake batch dimension. Okay, let's note this. Really good note here. I have stumbled across doing this sometime and making like I want an inference and I only have one input, but I need to have that 4 channel, the samples channel. So very good to keep in mind that is input. Doing this solves the problem. Okay. Great. Before proceeding further, let's recap all these classes you've seen so far. So the recap says that Torch.tensor, a multidimensional array with support for autograd operation like backprop, also holds the gradient with respect to the tensor. A net module, the neural network module, convenient way of encapsulating parameters with helpers for moving them to GPU, exporting, loading, etc. And parameters, a kind of tensor that is automatically registered as a parameter when assigned as an attribute to module, autograd function, implements and backwards definition of an autograd operation. Every tensor operations at least a single function node that connects to a function that created a tensor and encodes its history. Great. At this point, we covered defining a neural network, processing inputs and calling backwards. Still left computing the loss, updating the weights of the network. Awesome. Let's notice. Put this here. So I think it's really cool. I might later make this a little bit pretty. So we have the loss function. Okay. A loss function takes the output target pair of inputs and computes a value that estimates how far away the output is from the target. There are several different loss functions under the NN package. As simple as is the NN mean square error loss, which computes the mean square error between the input and the target. For example, let's go over the example. So you have the output of the network as net input using the same input as before. Target is equal to, this is like the labels of the example. Here we have target.view. I don't quite. Well, we are making the same as the shape as the output, as it says there. Criterion. Here, I don't know why we are renaming the, but we are going to do it this way. And then the MSC loss, or maybe. Let's see if this works. I think it should work, right? Okay. Weird. I don't know why you need to do this, but alright. So now if you follow loss in the backward direction using its if you follow loss in the backward direction using its .graph function attribute, you will see a graph of computation that looks like this. So when we call loss backward, the whole graph is differentiated with respect to the loss and all the tensors in the graph that has required grad true. We have there .grad tensor accumulated with the gradient. For illustration, let's use the follow as few step backward. Okay, let's see. Give me a moment here. All right. So let's print this to see loss grad function. Or have the MC loss backward. Print loss grad function next functions double 0 is supposed to be the linear. Add the TMM backward. We chop this down. And we do it again. This is the value. Accumulated grad. All right. Yes. All right. Back prop now. Let's see the back propagation thing. To back propagate the error, all we have to do is to loss.backward. You need to clear the existing gradient though, else gradients will be accumulated to existing gradients. Oh, okay. That's not that. Every time you do loss backward, we need to clear the existing gradients, else gradients will be existing gradients. Alrighty. So we zero the gradient, that's not it. And we do loss backward. Well, I was lazy and didn't do this, but let's see the output here. So the output was all 0 here. Before the 0, and hold on, no, the other way around. It's all 0 because we make it 0, and here it's added. Okay, so we only need to go loss backward, and the gradient is stored in the gradients. In the gradients of every parameter. Let's copy this because it's important to see, and let's know that after doing loss.backward, the gradients are stored in each parameter grad variable. Oh, there you go. All right, so what do we have next? Says, I think we are going into the last part of this. Now we have seen how to use loss functions. Read later. The neural network package contains various modules and loss functions that are for building blocks of deep neural networks. A full list of the documentation is here. The only thing left to learn is updating the weights of the network. Beautiful. update the weights. Let's see here. Well, this is general. This is huge. Okay, that's all right. Where the ball didn't work. There you go. So it says the simplest update rule used in practice is the stochastic gradient descent. Let's note that the simplest update rule used in practice is the gradient descent, SGD, and is going to use this to note weight equal to weight minus learning rate times gradient. Okay, we have it. Awesome. I think if you just do that, it's yes, that's better. You can implement this using simple Python code. Learning rate equal to 0.01 for f in net parameters. F data sub, so we are doing in place, subtraction in place. F dot grad dot data times learning rate. Great, and we did it. However, as you use neural networks, you want to use various different update rules, such as SGD, nested of SGD, Adam, ERMS, prop, etc. To enable this, we build a small package, Torch Optim, that implements all these methods. Using it is very simple. Oh, okay. So the Torch.optim package does this for us, and it also has other the different update rules, such as SGD, nested of SGD, Adam, ERMS, prop, ... So import Torch Optim as Optim. We create the optimizer. And we give it the network parameters, learning rate, and it says in your training loop, do optimizer 0 grad, 0 the gradient buffer, and we do that in the optimizer. That's something to keep in mind. So optimizer dot 0 grad. Then we do output of the network. I'm going to note that this is in the training loop. All right. What else? Network input. We have the output of the network. We we compute the loss function using the output and the target. Okay, then we do the loss. We calculate the gradient using backward, and we do an update using a step in the optimizer. Awesome, this is great. Let's see if this works. Oh, great. So first of all, we set up the grad. We create the output using the network and the input. We compute the loss using the criterion. In this example, mean square error that is up here, using the output and the target. In this case, well, it's random, but in some cases it's going to be the labels. We calculate the gradient using the loss backward, and finally we do a step in the optimizer to update the weights. So here we update the weights. Here calculates the gradients. Here loss gradients, output, and starting fresh. All right. Let's read this note. Observe how gradient buffers had to be manually set to 0 in the optimizer 0 grad. This is because gradients are accumulated as explained in the back propagation. All right. Awesome. I think the last one is training all of this. I think I will not have, it's already 2 hours for me. I will not have time for this, but next time we're going to consolidate all of what we learned here in this with this tutorial, and also going to continue with other ones. Let's go to the tutorials. So we did the 60-minute bliss, and then we're going to go for learning Pytorch with examples and going through each one of these until we don't have any more. And then we can do like project, but that's for in the future, so we're going to worry about that. To tease a little bit, we're going to learn Pytorch with examples. And let's see, we're going to have a bunch of examples here to learn from, and also a lot of smaller ones here. Oh, no, I mean, yeah, okay, awesome. So that's it for it now. Thanks for watching, and if you like this type of thing, please follow me and subscribe if you want. If you want to contact me, make a comment, or I have a Twitter, so I'm at ramchendeploy. Follow me, or I don't know, tweet me something. I always am there. And yeah, so people, hope you're doing well, and I see you in the next one. Goodbye.